Any questions before I begin, before we get into chapter 8? Ready? All right, let's do it. All right, so chapter 8, sequences and series. The name of the chapter is series. Chapter 8 is called series. And the first thing we're going to talk about in chapter 8 is something called sequences. Make this a little bigger here. First, we need to define what a sequence is. Now, look, all of these definitions are available to you, so don't be, trying to copy all these things down. A sequence is a function, all right? It's a function. We've been studying functions for a long time. The thing about the functions we've been studying in the past is that the functions we've seen, you plug in a number and it spits out a number, right? And the number we plug in can usually be any number, any real number. Like if I give you the function f of x equals, let's say 2x, right? That's a function. And I could plug 0, half, right? I plug in 1, 4, 1. I can plug in pi if I want. But the sequence is different. Okay, it's a function that goes from n into r. Now, n is the natural numbers. So it's taking numbers that come from this set. This is our new domain. So the things that go into the function can only be the number 1, 2, 5, 6, 7, 8. Not allowed to plug in 1.5. You're not allowed to plug in 0. You're not allowed to plug in -2, right? So that's it. That's the definition of a sequence. It's just a function with a restricted domain where that domain is the natural numbers instead of anything. All right, that's it. Simple definition. Questions? Notation. So traditionally, write f of x, right? To notate a function. For sequences, we change the notation. And I'm going to change the notation, but I'm going to do it in steps. The first thing I could do is say, all right, instead of this, I could write f of n equals 2n. And then that would look a little different than this. I'm using n instead of x. And now you know that the variable n, the input, is a natural number. So that kind of tells you I can only plug in 1, 2, 3, 4, 5, 6, 7, 8, 9. Understand? That's one way I could do it. But we do even more than that. We don't even use the f out here. What we do is we write a, and we subscript it with an n. Instead of using an f as the name of the function and then in parentheses the n, we replace like the f with a, and instead of using parentheses, we subscript with an n. And then we write over here 2n. That would be the way that I define a sequence. A sub n equals 2n. Now the advantage of this notation is that if you wanted to just start getting what the outputs of this sequence are, what would be the first number you plug into this? 1. So I could write a sub 1 equals 2 times 1, which is 2. And then a sub 2, that would be what I get when I plug in 2, right? Would be 2 times 2 is 4. And then a sub 3, 2 times 3, you get the idea, right? 2 times 3 would be 6, and so on and so forth. And these, I just start listing these out. It would just be a list of numbers, like a sequence of numbers, right? It would just be a sequence of numbers as an output. So my a sub n is actually just a sequence, a list, okay? We use a brace to start the list, and then we start listing out the first one, the second one, the third one, the fourth one, the fifth one, right? So these are just like the outputs of the function. Understand? So as an example, if I define the sequence a sub n to be equal n squared, and then I say write out this sequence, you would plug 1 in first. 1 squared is 1. Then you plug in 2. 2 squared is 4. 3. 3 squared is 9. 4 squared is 16, and so on and so forth. See the dot, dot, dot? The dot, dot, dot implies that that just continues forever, right? Feel good? All right, finite versus infinite sequences. Is this big enough? Is that, oh, that's a little better, huh? Finite versus infinite. So when you write a sequence, and you want it to just keep going forever, then there's a couple of notations. You can just write a sub n, and then it's understood that n starts at 1 and goes forever. Or you can write it with a set of braces around it. That would mean the same thing. Or you can write a sub n, and then on the outside subscript n equals 1, and then stop at the top to infinity. This gives you like a starting and a stopping. They all mean the same thing, though. If you don't write this, it's implied. Or you could write a sub 1, a sub 2, a sub 3, dot, 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 and then close your bracket. Got it? Now, a finite sequence is a sequence of numbers where you actually want to maybe start and stop somewhere. So the notation for this would be a sub n. Well, you could write a sub n, and then you can tell me n is always smaller than or equal to some number. So that means you're going to start at 1 and stop at k. Here, start n equals 1 and stop when I get to k. So I'm going to go the first one, the second one, the third one, dot, 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 stop when I get to the kth one. I'll give you an example of that. Specific example, if I give you n squared, that's the sequence. And I'm going to do n equals 3 to 6. This would be what? 9, 16, 25, 36, right? There we go. That's it. It's a finite sequence. Start somewhere, stop somewhere. You see the notation? Now, in this class, Cal 2, almost exclusively, we're going to be working with infinite sequences. There is a point when we're doing some stuff later where we're going to have to take what's called an nth partial sum, which means we're going to stop the sum. We're going to stop adding at some point and only look at that partial sum. So we will stop it from being infinite. But for the rest of today, and until I tell you again, it's going to be infinite. All right, just keep going. All right. Now, in order for you to be successful in this chapter, you've got to become very comfortable with the common sequences, the sequences that show up all the time that we need to keep on using, right? And so what I'd like to do is now, it's like a little game we're going to play. I'm going to put the sequence on the board, and you're going to have to come up with the formula for it. The formula that generates the sequence, all right? And we're going to take turns. Nobody's going to shout out answers. Everybody only gets one response until everybody in the room has responded. These are going to start out easier and get harder. So if you're nervous about it, try and go after the earlier ones. So I want for you to find a sub n. I want the formula for this. First example. All right, who wants that one? What formula generates that? Your first. Okay, a sub n is what? A sub n, it is the same thing. So what's the formula of them? N squared, right? N squared. Yeah, so it would be What do you get? Plug in 1, you get 1. We plug in 2, 2, 3, 3, right? There it is. Okay, good. Yes. Output. Oh, yeah, your output. So a sequence goes from the natural numbers into the real numbers. Your output can be anything. Your input has to be either 1, 2, 3. Okay, good. All right, so you're out of the game for the rest of the until everyone's gone. Yeah, a sub n equals A sub n equals n plus 4. All right, Andy, you're out. Does everyone see what's happening here? These are just going up by 1 each time, right? By 1 each time, just like this one did. Went up by 1 each time, but we wanted to shift where we started. We wanted to start at 5 instead of starting at 1. So what we had to do is basically add 4 to each of those numbers, and it created this list. That make sense? Who's up? Minus 4. What do y'all think? Yes or no? Do these go up by 1? Are we adding 1 each time? We're adding 1 each time, aren't we? But where are we starting? Right? So we need to subtract 4 to start us out at -3. Good? Yes.
Is there like a certain number of that's required for in order to
enough for you to see the pattern?
Okay.
Yeah.
Okay.
I should say that sequences are not unique.
Yeah.
So there you could have a sequence that has different formulas and they could be equivalent. All right, keep going here. How about this one? What's up? Go ahead. 2n. These are all what? So they're all even numbers, right? These are the even numbers. They all should be multiple of 2, right? So look, remember how these jumped up by 1 each time? And these are jumping up by 2 each time? See, that number in front is kind of how much the jump is. So this jumps by 2. Over here, this jumps by 1, right? These jump by 1 as well. These jump by 1 as well, right? And then all this number out here does is just kind of moves us back and forth somewhere along that list of numbers. If you write the what? Oh, okay, I see what you're saying. Like above this is 1, that's 2. Yeah, if that helps you, you can do it that way. All right, who's up?
Minus 2.
Okay, 2n minus 2. Yeah, so that's just, again, they jump by 2 each time, right? But we're starting at 0. So, you know, what happens if you plug 1 in here? 1 is 2 minus 2 is 0, right? Got it? These are very important sequences, these two, because they both generate even numbers, right? One of them starts at 2, the other one starts at 0, right? How about this? The odds. Okay. 2n minus 1, good. Isn't every odd number here just 1 less than every even number? So like 1 is 1 less than that, 3 is 1 less than that, 5, and so on. So 2n minus 1. Plug in 1, you get 2, take away 1, you get 1. Plug in 2, you get 6, take away, oh, sorry. Take away 1, 3. Yes. Not every single one of these. A lot of them aren't. I'm showing you the most important ones right now. How about this? How about, I don't know, -3, -1, 1, 3. You're jumping by 2 again, right? So you said 2n, a sub n is 2n minus 5. Y'all agree? That work? So in my experience with this class in this particular section, students are either like getting it or they're not getting it. Like they're either like seeing it like straightforward or it's like really abstract. It's hard to teach a student how to see it, right? Let's keep going. How about this? So. By then. How much are they jumping by? You're adding 5 each time, right? So these are all multiples of 5, starting at 1. Are you getting the pattern here? If you can find like the common jump, what is going to be the coefficient in front of your n? And you add or subtract a number to either shift it further, forward or downstream, upstream or downstream. Kind of like a shifting of a graph. Yeah. Exactly. All right, you get the idea? Okay. This is a really big one. Your first introduction into what's called an alternating sequence, because the signs alternate. Negative, then positive, negative, then positive, negative, then positive. This one's usually a little harder. So someone who hasn't gone. We haven't gone? Negative 1 to the n. Oops. Negative 1 to the n. Do I have to put parentheses? Yes. To the n, right? If you write negative 1 to the n, then this really means take 1, raise it to the n power, and then make it negative. You have to have the parentheses there. Does that work? What happens if I plug 1 into this? What's negative 1 to the 1? Negative 1. What happens if I plug 2 into this? Negative 1 squared, that's going to be positive 1. Negative 1 cubed. Odd power. So odd power is giving you a negative, right? Giving you a positive. Using the cyclical nature of negative 1, that it keeps cycling as you raise it to different powers. And we're using that to create that. Yes.
Could you also use the sine, cosine?
You could, but I think that would be not as simple. It's a little bit easier to use this. Do y'all remember that problem I gave you, or one that you had presented? Yeah. I offer that. Oh, I gave it to my Cal 3 class. That's right. I gave that to my Cal 3 class, and it was a problem that involved inclinating like this, and a bunch of them use cosine and sines, which is fine, but it made the formula much more complicated. So, okay, let's see. How about if I wanted to do? Tell me. Let me ask you this. What if I change this formula? Would me changing this to this, would that change the formula at all? Does that make any difference? Because when I plug in 1 here, what do I get? Odd. And when I plug 1 in here, I get odd. And then when I plug in 2 here, I get even. And when I plug 2 here, I get even. So that makes no difference in the formula. That would still generate that, wouldn't it? Yeah. And what if I do this? Negative 1 to the n plus 4. Same thing, right? So couldn't you say that this is really like a sub n equals negative 1 to the n plus or minus an even number? Yeah, you could use words, right? I mean, just it would work, right? If I do n and I do plus nothing, that's an even number. 0 is an even number. Plus 2. Does it work if I do minus though? Hold on. What if I do minus? No. What if I do minus 4? But what's negative 1 to the 0? 1. So it still works. Still works. Try it. Let's plug in 1 here. What happens if you plug in 1? What do you get? Negative 1 to the 3rd, right? I'm going to create this one. I'm going to do this one separately. Negative 1 to the 3 is, and then now it would be negative 1 to the what? plug in 2, oh, -3, thank you. Oh, and then plug in 2, you get -1 to the -2, and then -1 to the -1. Do y'all see what I'm doing?
Oh, yeah.
Yeah, so, but what does that really mean, right? That really means -1 to the 3rd, but that,
Yeah.
right? You drop that down, you drop that down, you drop that down. So let me go one more, -1 to the 0. So the next one will be 1 over -1 squared, then the next one is 1 over -1 to the 1st, and the next one is 1 over -1 to the 0. Actually, I don't need to drop that one down. -1 to the 0. So this is what? -1, 1, -1, 1, and it'll keep going. So, plus or minus any even number, and I'm going to create an alternating sequence starting at -1. What if I want my sequence to start at +1? So positive, negative, positive, negative. Who wants to do that one? Oh. So if I want 1, -1, 1, -1, 1, -1, right? Dot, dot, dot. Have you gone? How do you see this? To the n plus or minus any odd number. Let's do a specific one. We'll put that back in a second. Let's do n plus an odd number. Let's do a simple odd number, 1. That's the one we use the most often. Frequently, that's the one we use to create that. So what happens if you plug 1 in here? You get a 2. And now -1 squared gives you a +1. And when you plug in 2 into this, you get a 3. -1 third gives you a negative number. Plug 3 into that, you get a 4. So it just, hey, wait a minute a second. Hold on a second. Hold on a second. Isn't that properties of exponents? That turns into this, doesn't it? Like if, yeah, that's the same thing, isn't it? And that created the list starting with negatives, right? Negatives, -1, positive. Negative. All of those by -1, which changed the signs of the previous one. So it just took this and multiplied each of these by -1, which changed their signs. So I can do that, and then you can do either plus. Let's see. How about this one? What's it? Amount each time, like the previous ones were right. Previous ones, like it jumped by 1 each time, or jump by 2, or jump by 5, right? That's not what's happening here, right? We don't have a common jump. By the way, those other ones are called arithmetic sequences because there's a common jump, but I'm not going to get into oh, yeah. Tell me what you're seeing here. Anything that you see? Like, how are any of these numbers related to one another? Whoa. They're multiples of 3. They're all multiples of 3. So this is 3 times 1, right? This is 3 times 3, 3 squared. This is 3 times 3 times 3. That's 3 cubed. This is 3 times 3 times 3 times, right? There's 4 of them. So could I not write it this way? Let's get back to the 1 in a second. 3 to the first power, 3 to the second power, 3 to the third power, 3 to the fourth power. Could I not write it that way? And then this right here would have to be, if it follows the pattern, this would have to be 3 to what power? 0, and 3 to the 0 is 1, right? Following? Everyone see that? So the formula here is that the base is always 3, right? The question is, what's the power? Look at these powers. 0, 1, 2, 3, 4. Isn't that just our counting numbers? How do we create a jump by 1 starting at 0? Who said that? I'm trying to get one person, okay? If everyone blurts out the answer, I'm trying to help one person think through it, all right? All right, so n, if I do n, right, that sequence by itself, that's 1, 2, 3, 4, 5, 6, right? If I take 1 away from that, I get the 0, 1, 2, 3, 4, 5, 6, right? So I'm going to put n minus 1 up here.
And it was started.
It would have started there, right? If that was just n, it would have started there. It would have been 1, 2, 3, 4. We wanted it to start at 0, so we put an n and take away 1. Make sense? Yes.
So if you're given Asian polynomial, I guess because we were just starting with I can change that and make it start at 0 necessarily.
Make it start at 0. I'm not sure what you're asking. Is that you have that relation? Oh, yeah. Yes, I understand what you're saying. Could I have done something where I just change where I start instead of always making it start at 1? I could. However, we are going to want to always start at 1 if we can. The changing is if we want a finite sequence, it's nice to be able to control, but we want everything to start at 1 because where we're going with this, it's going to start at 1. Like we're going to be starting at 1 every time. All right, let's do another one. So how about any volunteers on this one? Yeah.
So, like to make the problem solve for these questions is like what you did before we had like the
build this in pieces. Can we kind of like analyze this and think about it more as like different things happening as opposed to trying to getting the overall? We see it's alternating, right? Alternating. Negative, positive, negative, positive, negative, positive, right? So we have that. Do we know how to make something alternate? Yes. Do we know how to make it start with a negative, then go positive, then negative, positive? Yes. So I would start this by saying, all right, I've got -1 to the n. That's going to start me with a negative number, right? Negative, then positive, then negative, then positive, negative, positive, right? So now what I can do is I can look at this again, but I can ignore the positive and negatives, or just ignore the negatives, I should say. Forget that, forget that, forget that, because I'm taking care of that part with this. Understand?
Then you're asking the question of how you're going to 1/2.
Yeah, so how can you generate this sequence of numbers, ignoring the negative signs? There's something about all of those numbers. So who is what all those numbers have in common? We're just gonna go around again. Do you see what they have in common? So what do you see? Okay, so the next one here, yeah, it is 16. Yeah, it's multiple. So it's this, you got it right, but the best way to formulate that is by using exponents. Like these are all multiples of 2, right? Which means these are all powers of 2. This is 2 to the first power, 2 squared, 2 cubed. That makes sense? So if this is 2 to the 1, 2 squared, 2 cubed. Following that pattern backwards, let's see if it works. Is this 2 to the 0? Well, anything to the 0 is 1, right? And then that would have to be following the pattern 2 to the -1. Is it? It is, right? 2 to the -1, you drop it down, it becomes 1/2. And minus 2, exactly. So 2, so you say times 2 to the n minus 2. So all of these are powers of 2, but we want to start at -1. So if I plug in 1 in here, I get 1 minus 2 is -1. And then I can leave it like this. This is fine. I can just leave it like that, or I can start trying to put things together. I like just leaving it just like this. If you wanted to put it together, and do something else, you would do this. So you split this into 2 pieces like that using properties of exponents. Do you all agree that's how that would split up? And these are both to the same power, aren't they? So I could write that as -2 to the n, and then this I could write as 1/4. Just drop that down. That would be another way to look at that form.
Yes. So and the sign split and for -1 to n is generally
yes. It would have started positive, then negative, positive. If it was positive, negative, positive, negative, positive, negative, I would have used -1 to the n plus 1 or something, n plus an odd number. So that's why I said this is such an important sequence, because it's what we use whenever we have alternating happening. So when I put this up on the board initially, I would never expect anyone in the class to say, oh, that's 1/4 times -2 to the n. Nobody's going to see that. What they're going to have to do is break it down and go, oh, yes. And then you mean just write it as this with what next to it?
and then it's minus like n minus 2.
Oh, no, you can't. Oh, wait, no, because they don't have the same, these don't have the same. You either have to put these 2 together and get that separated with this, or you put these together because they both have the same power, but you can't put all 3 of these together because they don't all have the same base. I'm not sure if that's what you're asking me. I think what you're asking is, can you do this? This is not, this means what? -2 to the n times -2 to the -2, right? Because it's squared, I guess you could, because it's squared. Squared. The way you just drew. That would turn out to be positive. This is positive 1/4. Turns out to be, this is positive 1/4. Right? This is 1 over -2 squared. That's what that is. But that's 1/4. So it turns out the same because it's squared. If it was something else, it would not. It wouldn't be able to do that. Yes, that's why just leave it there.
I was just going to say a weird observation. At first looked at it, I thought it was actually 1/2. But I realized once you got to 3,
it does.
Or it doesn't.
Yeah, 1/2 to the 3rd would be 8. Well, if 1/2 to the negative. So if you do 1/2, right, to the -3, I don't know if this is what you mean, but
oh no, I meant like
oh,
not the power, but like that. as a coefficient.
Oh, okay, got you,
Yeah, so
okay.
that's what
There is a way you could have done that. Those are all powers of 1/2 as well. But it'd be a little bit harder because your sequence would have to go backwards up top. So let's not do it. We've got our answer. Let's see. How about this? How about 3/2 minus 5/4 plus 7/8, or not plus 7/8, and then let's go negative 9/16, ... Who's that? Madison? How do you feel? You want one more time to look at it, or is there anything you can see that's like obvious in terms of, how about signs? Changing, starting positive, then negative, then positive. Okay, so how would we make that happen? -1, okay, to what power? And +1, there you go. Okay, so that's going to take care of the alternating, right? That takes care of the alternating. So let's ignore the alternating now. And let's just look at the numbers. All right, somebody else? Who hasn't gone? That table hasn't gone. No? Yes? We gone? No, you've gone, right? Yeah. You've gone. You haven't gone? Oh, you've asked questions, though. Well, that's why we're doing this. That's why I'm putting you on the spot. I'm going to help you see it. Now, I think maybe what you're doing is you're looking at these as fractions right now, which makes things really hard. Just look at the numerators for a second. Tell me about the numerators. Well, they go up by 2 each time, right? So 3, 5, 7, 9. Those are the odds, right? Starting at 3. Can you do that? They jump up by 2 each time, right? So I'm going to say, I'm going to look at that fraction on the side. This is a fraction. This is taking care of my alternating. All the numerators are even powers, so they jump by 2 each time, so 2n, but that needs to start at 3, right? So what would I need next to this? Because right now, if I plug in 1, I'm going to get 2. I need it to be 3. +1. Look at that for a second. Plug in 1, what do you get? 3. Okay, now plug in 2. What do you get? 3. 9, right? Okay, so you got the top taken care of. Now look at the bottoms. 2, 4, 8, 16. Those are not jumping up by 2 each time, right? They're not adding 2 each time. It's 2 to a power, right? This one right here is 2 to the first, 2 squared, 2 cubed, so on and so forth, right? So you need 2 to the n. If I start at 1, I get 2. If I get 2, I get squared, right? 3, there you go. There's your formula. Does that make better sense?
Yeah, that makes sense.
If you just try and look at it as fractions, you're just like trying to it's too much. You have to kind of chip away at it piece by piece. What do y'all think? Yes. These, okay, so I have, if I just look at the numerator, 3, 5, 7, 9, right? That looks like the pattern I have there. These are all jumping by 2 each time, right? Anytime you add 2 each time. So I put 2n. If these went up by 3 each time, I put 3n. If they went up by 5, then I do 5n. So they jump by 2, and then I need to start at 3. So I needed to add 1. Start at 3.
There's a lot of these with even numbers like a base. Is it better if you look at how far something is? Like in that case, yeah, not as easy to see as 5, 7, 9. But
Well, I mean, if they jump by 2, then yeah, but I mean, I could have, if I wanted to, start this out and did 5, then 10, then 15, then 20. You know what I mean?
yeah.
So I just picked two to pick two because we're messing with it, right? The big takeaway here is, can you start to see patterns or not? That's what we really want to be able to do is, I give you something, can you see the pattern? Can you recover the formula from the pattern or not? That's a different way of thinking, right? That's a different type of thinking. It's not a like a monkey see, monkey do type thing. It's a, do you understand what's going on here? All right, let's continue in the notes. We could spend all day doing those problems. Let's see. I've got some more stuff for us to look at. I think I have a couple of take-home problems that are really hard. Yeah, but we can really bog ourselves down just like throwing some crazy stuff out there. So let's look at the common sequences in my notes. So first, the integers, right? This creates, 1, 2, 3, 4, 5. That's a sub n is n, and then n plus 3. That's going to be the integer starting at 4. N minus 5. We did all these, right? Even integers, even numbers. Now we can add or subtract to shift that. Okay, 2n minus 1, odd numbers. Then we can do odd numbers by shifting, right? These are the alternatings, the big alternating ones we need to know. This one alternates, starts you at negatives. This one alternates, starts you at negatives. We can add or subtract an even number. And then here's there's the alternating starting with positives. Or you can add an odd number to the end. So those are the basic ones. Then there's some other ones. K times n. So if this number in front is 5, right? Then we're going to go 5, 10, 15, 20, 25, 30. Whatever that number is in front, those are your multiples in there. And then powers, we did this, right? Actually, yeah, we did this, like powers of 5. So 5 to the first, 5 to the second, 5 to the third, 5 to the fourth. Gives you all the powers of 5. This is a little different. This one, the n is in the exponent. Down here, n is the base. So if I did n cubed, it's 1 cubed. The thing that's changing is the base. So it's 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed. It's harder to see that here. I think this is a hard sequence to see. But this is 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, right? That's a little harder to see than, for some people. All right, alternating sequences. An alternating sequence is any sequence that goes negative, positive, negative, positive, negative, positive, or it goes positive, negative, positive, negative, positive, negative. And we've seen with the examples how we handle those. We just throw this -1 to the n out front, or -1 to the n minus n plus 1, and that'll create the alternating for us, right? All right, now we talk about something called factorial, which some of you have seen, hopefully, maybe not. So when I write this 4 factorial, do y'all know what that means? What does that mean? Yeah, this means 1 times 2 times 3 times 4. Or I'm going to write it the other way. I'm going to write 4 times 3 times 2 times 1. So 4 with an exclamation point is the mathematical notation used to represent this product. And this is defined for all of the natural numbers. So you did 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1. It's just a condensed notation for something that's kind of hard to write out. What's 1 factorial? 1 times 1, so just 1, right? It's just 1. Okay, here's the tricky one. Not tricky, but the weird one. What's 0 factorial? Now I realize 0 is not a natural number, but I'm asking you, have you ever seen that? Do you know what 0 factorial is defined to be? 1. Okay, so this right here confuses students. And I understand why it confuses you, because it doesn't follow the pattern, does it? It doesn't follow the pattern. And so when you look at that and you see it, you're like, well, wait a minute. If the rule was, you know, start with that number, and then just start going down till you get to 1, then that you should start with 0. That should give you 0, right? But I'm here to tell you that the factorial is actually a different function than this. This is the way that makes perfect sense. This makes sense to us, but there's another function called the gamma, which is actually where this all comes from. And the gamma function can handle this, like 1/2 factorial. That's defined. For us in this class, this is not defined. You have to put natural numbers in here. Okay, but for a math major, you go and learn about this thing called the gamma function, where this is defined with the gamma function, and you can get an answer. And the gamma function will also take 7 factorial and give you the correct answer the way we define it here. Okay, so it matches up at all the natural numbers. At all the natural numbers, the gamma function gives you the same answer as the factorial, the way I have presented here. And the gamma function here will give you 1. So, but it's beyond the scope of this class. Yes.
So 2 questions. So just class, we just have to remember.
So this, whenever you're given something, it doesn't make a whole lot of sense. You usually put a colon in front of the equal sign, and that tells you that I'm defining this. Okay? Defining this, don't ask questions, right? Like this is defined to be 1. If you really want to understand, I think I'll just show you, okay? Because a lot of you have never seen the gamma function before, right? So gamma is a pretty generic word, right? Yeah, it's Greek. So this is it right here. Using the very reliable Wikipedia here. But I know what Wikipedia says on this, and it's correct. So well, before I answer that, let's look at what the gamma function's definition is, all right, before I answer that. So if you take, this is the gamma function, gamma of n is the same as n minus 1 factorial. So in other words, if I take gamma of 3, that is equal to 3 minus 1 factorial, which is 2 factorial, which is 2 times 1, which equals 2. All right. Right? Hold on. I haven't defined what gamma is. Okay. This is the definition of gamma. It's an integral. We're defining a function as an integral. It's the integral from 0 to infinity. So it's an improper integral. All right. You're integrating with respect to the variable t. So that's t. That's t. The z right here is a number that is the number you're plugging into the factorial. So I'm going off on a tangent, but shit, we're here already. So let me do something here. Oh, come on. Come on, hurry up. Why is that so damn slow? So I'm going to do something easier, all right? Let's do gamma of 2. Should be 2 minus 1 factorial, which is 1 factorial, which should be 1. That should be the answer. So let's go over here, and this right here, I'm going to replace with 2, which means I'm going to replace that with 2, all right? So it becomes the integral from 0 to infinity of t to what power? 1, and then e to the negative t dt. How do you integrate that? By parts. You know, So if I did parts on that, I would choose this to be my T. This would, that would be my U, and then this would be my dV. I'm going quickly because we don't have time. The derivative of that is dt, and the antiderivative of that is negative e to the negative t. You have to have a negative there because of the chain rule. And then now I do ultraviolet minus voodoo. So this times this, t times negative e to the negative t, minus the integral of voodoo, these two, right? Voodoo, bring the negative out, that'll become plus, and then e to the negative t dt. And that will turn into negative t, that's this, e to the negative t, and then plus this integral, but the integral of that, or antiderivative, is negative e to the negative t. That's my antiderivative. And now I want to evaluate that from 0 to where? Infinity. Now that means I have to take a limit, right? I have to take a limit. So let me do one more step. More step would be, let me rewrite it. This is negative t over e to the t minus 1 over e to the t, evaluated 0 to infinity. All I did there is just drop the negative exponents on those e to the t's down, right? Okay, let's let t go to infinity. What would this go to? T goes to infinity. Yeah, it'd be infinity over infinity, right? One time, and you would get 1 over e to the t. So that's going to go to 0. And then t is going to infinity. So infinity over infinity. L'Hopital, one time, turns into 1 over e to the t. What is one time? L'Hopital's rule? To the top and bottom separately. So L'Hopital gives us 0 here. And then 1 over e to the infinity, that's 1 over infinity, that's 0, right? So when we go to it here, that gives us 0. Minus, okay, now let's plug in 0. 0 into that, 0, e to the 0 is 1. Gone. E to the 0, 1, minus 1. So we get minus 1. Minus 1 is 1. Okay, and that's what 1 factorial is, right? 1 factorial is 1. So gamma of 2 is equivalent to 1 factorial. That's right. That's right. If you want to find n factorial, you plug n plus 1 into gamma. Now, the beauty of the gamma function is that you can feed it any number. So what if I wanted to know what gamma of 0 was? I'm sorry, gamma. What if I wanted to know what 0 factorial was? Right? Let's do gamma of 1. What would happen if I plug a 1 in there? I get 0 there, right? T to the 0 is 1. So now this becomes this integral. Right? Because the T to the 0 is 1. And that integral is super easy. That's negative e to the negative t, evaluated 0 to infinity. And that's the same as negative 1 over e to the t, evaluated 0 to infinity, dropping that down. If I go infinity in here, negative 1 over infinity goes to 0. Minus, and if I plug in 0, I get negative 1. And I get 1 again. So 0 factorial is gamma of 1, right? It's defined to be 0. So when we say 0 factorial is 1, take it on faith, it's because of this. Again, the beauty of the gamma is that now 1/2 factorial makes perfect sense. 1/2 factorial, because all I have to do is come in here, replace this with 1/2. And so this integral will be t to the negative 1/2. And then whatever that is, okay? You have to go figure that out, but there's an answer. And if you graph the gamma function, this is the graph of the gamma function. Look, really, you need to look at the right side. The right side. The gamma function is defined for all real numbers, right? So if you plug in, 2 into gamma, you get 1. If you plug in 1 into gamma, you get 1. If you plug in 3, you should get 6. But you can plug any other number in between those in and get answers as well. Okay. So anyway, we are going to move on. Sorry, that went off there a little bit. I just, you know, if I can explain why 0 factorial is 1, I'm going to try to. So here's the definition of factorial not using gamma, right? Not using gamma. Is that if we, for n bigger than or equal to 1, we define n factorial to be n times n minus 1 times n minus 2 times n minus 3. You keep on subtracting 1 from the number until you get to 1, and that's when you stop. So what is it that we need to know how to do in here with the factorial? Some special properties. This is probably the most important one. If I write n plus 1 factorial over n factorial, then what this means is that you start with n plus 1, then you take 1 away from it, it becomes n. Then you take 1 away from that, n minus 1. Then you take 1 away from that, n minus 2. And you keep doing that till you go down to 1, right? That would be what the top is, right? When I do 5 factorial, this is 5 times 4 times 3 times 2 times 1. So every step I go, it's going down by 1 each time. That's all I'm saying here. Whatever this number is, I start with that one. Then I multiply times the next number, which is 1 less than that. What is that? Do I hear that? Music. You. Did y'all hear it? Yeah, I heard it. There, n minus 1, n minus 2, and I stop at 1. N factorial starts at n, and then take away 1, take away 1, take away 1, keep taking away 1. Do you see a bunch of those are common factors? Yes. Yeah, this is n. Just say fix n to be whatever n is. Yeah, it's fixed at n. If I fix the n, then this expression turns into that, right? And then a bunch of these cancel. And all you're left with is the n plus 1. So let me give you a specific example. 7 factorial over 6 factorial would just be what? 7.
Oh, okay.
Why? Because 7 times 6 times 5 times 4 times 3 times 2 times 1 over 6 times 5 times 4 times 3 times 2 times 1, 7. Right? That's the property. But we want to know the abstract form than this form. So let me see if you really understand that. What about this one? What's 3n plus 2 factorial over 3n minus 1 factorial? All right, so which number is bigger? Numerator is not. Numerator is bigger, right? You fix an n, numerator is bigger. Okay, so let's start writing out the numerator. As a factorial, you start with 3n plus 2, right? And then you multiply that times what? Take away 1 from that. So if you subtract 1 from that, what do you get? 3n, yeah, plus 2, take away 1 is plus 1, right? And that you keep doing this, right? Okay, 3, what would be the next one?
3n plus 0.
Just 3n plus 0, just 3n, right? And then I have to keep going, right? 3n minus 1, and I keep going, right? I don't need to keep going because look, would you all agree that the rest of the way down, if I put a factorial on this right here, right, that would mean I keep going from this, right? I keep going down. But isn't that what the denominator is? Yep. See, so the denominator is 3n minus 1 factorial, right? Everything else the rest of the way down cancel out. So I can just go ahead.
Cancel out.
You can cancel out the factors within a factorial. One of them is bigger than the other. I could have had written this fraction the opposite, and we still would have taken the bigger one and broken it down and it would have canceled on top. We would have been left with 1 over this. Yes.
So would you have a good question, but would you have been wrong to like input and say like
Yeah. Yeah, because you're not going to get you're not going to get the algebraic result. You'll get a specific result for that specific n, but you won't get the algebraic result of that.
like you wouldn't be able to find
Yeah. Nice, but for what we need this for later, it won't help you to plug in a specific n. We need it to be an algebraic expression. Yes.
So you were right.
The bigger one. So you get to the smaller one. See, I kept going down, subtracting one until I realized the bottom one and this one were the same. And then instead of continuing to write this, I put a factorial next to it to imply that that keeps going, right? But that's the same as what the denominator is doing. It's going from here and going down. So I cancel them out. Okay, yeah, I don't see the limit. I don't see the connection to limit, but oh, a limiting point, like okay, like a threshold. Okay, I was thinking limit, like you wanted something to go to infinity or something. Okay. Okay, good. All right, let's try and visualize sequences. Which sounds worse than it is. A sequence is a function that's been restricted. Whoa. I don't know what's going on. My voice has been doing that more lately. That's been restricted to the natural numbers, right? It's the only difference. So when we had, before, I asked you to go and graph f of x equals 2x, right? You would just graph a line, slope of 2, right? Just like that. But now if I ask you to graph or to plot a sub n is 2n, it's the same as that graph, but what? Yes, but you're only allowed to plug in 1. So I can plug in 1 and I get what? 2. And I plug in 2 and I get 4. If I connect them with a straight line? No, because that's not what a sequence is. A sequence is not a nice continuous function. It is only defined at points. You should expect a graph. All right. Sequence is just a bunch of dots. I'm not sure why that's giving me an error. So let's try and reevaluate this code. There we go. So what you're looking at here is a visualization of the sequence. This is the sequence a sub n equals -1 to the n times n squared. That's what you're looking at there. And so when we plug in 1, it's hard to see these, I'm sorry, but when you plug in 1, you get -1 to the 1 that's a negative, and then 1 squared is 1. So you get -1 when you plug in 1. So when I plug in 1, I get 1. When I plug in, when I plug in 1, I get -1. It's hard to see it here. When I plug in 2, I get 4, and then -9, then 16, then -25, then so on and so forth, right? Thank you. But notice there's nothing in between those dots, right? Nothing. Yes.
Is there ever going to be like a
Well, I could a sequence, I can give you a sequence of numbers that you wouldn't be able to come up with a formula for. Yes. I mean, you could just take the decimals of pi, like 3.1415, right? Do the 1,4, just do the 1,415, just do that as your sequence for pi. There's no pattern. If there was, we would have a formula for it, right? There is no pattern. So, yeah, yeah, I wouldn't touch anything like that with you in here, right? All right, there's an example, yes. Do I want more points? I mean, this goes forever, right? I can have more points in there. Yeah, I don't need to do any more of this. Okay. Another sequence. Harder to see this one. Let me write down here what this one is. This one is the sequence n squared over 1 plus n squared. When I plug in 1, what do I get? A half? Okay, let me make these points bigger so you can see them. Okay, there they are. When I plug in 1, when I plug in 2, I get 4/5.
Yeah.
When I plug in 3, I get 9/10.
Yeah.
The denominator is always 1 more than the numerator, right? So when I plug in 4, I get 16/17. I plug in 5, I get 25/26. When I plug in a billion, I get a billion squared over a billion squared plus 1. This is asymptotically approaching something, isn't it? Looks like it's approaching asymptotically, it's approaching 1. So let me make these points smaller. Let me go out further. Let's go 100 points out. Yeah, you see that? They're all kind of grouping up, getting closer and closer to 1. We never get there. 1,000 of them. Almost looks like a line. It's not a line. Or it looks like a curve. It's not. Those are little dots in there. So do you see that, you know, the previous example, they were like, you know, up, down, up, down, up, down. They're spreading apart like this. And then here's an example of the sequence where they're, it's kind of like, I don't know, like right? Headed to sort of converging to something, right? That's going to be a word we need to understand here. I'm trying to lead you to it here. Seems like this sequence is converging to something. The bigger that n gets, right? The bigger that n gets, this goes somewhere, heads to the number 1, right? You can see it visually. Okay, the limit of a sequence. That seems natural now, right? We want to see what's happening to the sequence as we go out forever. So given a sequence, A sub n, we will say the sequence has a limit of L if, when we let n go to infinity in the sequence, when we take that limit, we get L, provided the limit exists. It could turn out that the limit doesn't exist. If the limit does exist, then we will write A sub n with an arrow to its limit. So like the problem we just did right here, visually it looked like this was headed to where? 1. So the way I write that is n squared over 1 plus n squared. If I had proven it does, I would say with an arrow to 1. That is telling you that the bigger n gets, the closer this gets to 1. And in that event that we actually head to a number, we will say that the sequence A sub n converges to the number L. Okay, so that's what I said. That sequence converges to 1. If it doesn't converge to a number, then it diverges. So if you take a limit of this thing and you either get infinity or negative infinity, or you get a limit that doesn't exist, then you will say that the sequence diverges. So let's visualize convergence. That's convergence of a sequence, right? Further out you go, approaching some asymptote, right? Horizontal asymptote. This is also convergence, even though it doesn't look like it. It is. This is convergence. Our sequence is like up and down, up and down. It's going back and forth, but it's kind of like funneling in and just getting closer and closer and closer and closer and closer to 0. Even though it goes above and below, it's funneled in. That's another example. This is another example. There's like a funneling effect. Here's some that diverge. Yes.
Is there it's like there's a function in the
Oh, you're talking about the function like with real numbers versus the sequence. Great question. It's going to be a theorem. So just wait for a second. Here's an example of a divergent sequence. Why is this divergent? Doesn't go to a single number, right? It keeps hopping back and forth, right? This is actually a sub n equals, what is this? A sub n equals -1 to the n. Because when you plug in 1, you get -1, then 2, you get 1, then 3, you get -1, 4. This is a non-convergent sequence because it keeps hopping back and forth between -1 and 1. Theorem. Here it is. Does this make sense to you? Let's say that you're taking the limit of a function of x back from before today. Okay, so it's a function we can draw it without like picking up a pencil. What if you have some function, you go to infinity on that and it has a limit? Then do you agree that if we restrict that same function to just the natural numbers, then that should go to the same place? Like if I draw a curve, right? If I draw this orange curve and that orange curve heads to 0, then if I restrict that orange curve to just plugging in natural numbers, then the black is going to do exactly what the orange did. So that's a way that we can actually find limits of sequences. We can just convert them to the traditional functions of x, use all the rules we learned about limits in Cal 1, and then just apply them to the sequence. So whatever the function of x does, the sequence does. If the function converges, the sequence converges. If the function diverges, the sequence diverges. I would turn the sequence into a function of x and then take the limit of it. And then whatever that does, the sequence does. Let's do an example. The gamma function's cool, huh? You do what?
You have like
out of a sequence or a series? What are you talking about? Yeah. If it's a constant, it can come out. If it has n in it, it can't. Yeah. All right. How about this? What if I wanted to know what this sequence does? Does this sequence converge or diverge? From here on out, you'll probably see me write C/D ? If I want to ask for convergence or divergence, so I have to write that over and over, right? I'll say, does a sequence C or D, in that way. All right, here it is. A sub n equals, well, let's do the one we just did a second ago. Converges to what? How do you know? Because we looked at it, right? We analyzed it. We said, hey, yeah, look, it looks like it's going to 1. But now you need to prove it more formally to me. So what I'm going to do is I'm first going to convert this to a function of x instead. So I'm going to look at f of x equals x squared over 1 plus x squared. And now what I'm going to do is I'm going to take the limit as x goes to infinity of this. Whatever that limit does is what that sequence does. Whenever we're doing this, we always let x go to infinity. Because remember, our sequence, our n is the input, right? And it starts at 1, then 2, then 3, then 4, and it goes forever. So we're taking this limit on this function as we go to infinity. Okay, what is that limit? What do you get if you let x go to infinity in the numerator? Infinity, and on the bottom, infinity, yes. Yes.
Negative. So then you're supposed to have one and go like positive.
Oh, well, if I write infinity, this doesn't mean both sides. There's only one side to positive infinity. Yeah, so you're thinking like this was a 5, that means you have to come in from the left and right of 5. Because it's infinity, it's out there. There's no this side of infinity. Yeah. Okay. Gotcha. Yeah, now if I put a minus in front of it, now that's different. That's us going the other way. Okay, so we had infinity on top, infinity on the bottom, and when we have that, we use L'Hopital's rule. L'Hopital's rule. So I'm going to say equals, I like to put an L with a little circle around it to say I'm using L'Hopital. L'Hopital says I can take derivative top and bottom. So derivative top is 2x, derivative bottom is also 2x, isn't it? And 2x over 2x is 1. So limit as x goes to infinity of 1 is just 1 because there's no more x's. So our answer is 1, right? We're not done. Therefore, you'll see me write 3 dots like this in a triangle shape. That means therefore, okay? Therefore, a sub n equals n squared over 1 plus n squared, arrow to 1. That's me telling you that the sequence converges. I wanted to know, does this sequence converge? So then we looked at the function. When we did the function, we did the L'Hopital, right? And then we came to a conclusion that the sequence must do what that function does. Yes?
So if you're whatever the function.
Yes, whatever the function converges to, the sequence converges to. Now, why is it important that I went from this sequence to a function of x? Why did I have to do that? There's something subtle but important here. You can plug infinity in for n here. You could let n go to infinity. It makes sense to let it get bigger and bigger and bigger. That's okay. There's something else that we would have run into a problem with. Why do I have to change this? Why do I have to change this to a function of x and then do that work and then come back to n when I could have just, like, why not just do this and leave everything in terms of n? It has everything to do with the fact that this is a like x squared over 1 plus x squared. If you draw it, you don't pick up your pencil, right? Yeah. And therefore, if you draw without picking up your pencil, you have tangent lines, don't you? And don't you use L'Hopital? And L'Hopital requires a derivative, and derivatives means you have to have tangent lines. If you're looking at sequences of dots, if I give you that dot right there, can you tell me the slope of a tangent line? Yeah, the slope of a tangent line. Derivatives of functions.
In theory,
of x.
Same answer, but
exactly. In theory, had I left this n instead of L'Hopital and all that and did everything, I get the same exact answer. But I'd be wrong in the sense that you can't take the derivative of a sequence. Do y'all understand that? Yeah. Given that information, as I move forward, I'm going to skip this step. And I am going to do exactly what I said that I'm not going to do, because I don't want to write function goes to f of x every time. So I'm going to say basically this, I'm going to do L'Hopital, and I'm going to basically say with a little asterisk that really m changes to a function of x and then coming back. All right, it's just to save time. All right, let's look at another one. How are we doing on time? Well, I don't expect you to change it to f of x. I've stated it in class. I've made it clear that this is technically what's required to use the theorem, but in an effort to save time, we are just going to work with it as a sequence. How about this one? Over n. What happens is n gets huge here. Think about what happens. This becomes really big, right? And you're raising it to the 1 over a really big number is 0. So you get like the base wants to get huge, become infinite, and then your exponent wants to head towards 0. Right? So what happens in this particular scenario when you have something that's getting big, the exponent wants to head to 0? This is an indeterminate form from Cal 1. We don't know exactly what this does. We have to actually do some work here. It's like logarithmic differentiation. We're going to bring logs in and stuff. So now this is where I would technically want to switch this to a function of x. Right? Let's actually, I didn't write it down. Let's write this sequence out. What are the first few? Like plug in 1, what do you get? 1. Plug in 2, what do you get when you plug in 2? The square root of 2. What happens when you plug in 3? Cube root of 3. 4? 4th root of 4, kind of a weird, cool looking sequence, right? 5th root of 5, 6th root of 6, 7th root of 7, 8th root of 8, so on and so forth. Is that converging to something? We're about to find out. We're about to find out what if it converges. But the thing under the radical is getting bigger, right? So I don't know. I mean, I think it's a good argument to say it looks like it's getting smaller, but we have to actually do it, right? So the way we handle this is, again, there's a little asterisk here. Technically, I'm looking at this as like a function of x, but to save time, I'm not going to do it. And then the way we do it, and this actually does vary in your Cal 1, how it's shown to you. The way that I teach it, and if you saw a different way, then you'll have to do it your way or I don't know what you're going to do. You need to be able to get to the answer, whichever way you learned it. So the way I teach my students is that when we have this form, we take the, well, we have to take the limit first, right? We're trying to figure out what is the limit as n goes to infinity of n to the 1 over n, right? That's what I'm trying to figure out. What is that? And when I do that, I'm getting this form. So I tell my Cal 1 students, in this form, I create an equation out of this, and I call this equal, normally I put y here. So I said, we want to know what y is, right? We want to know what this limit is. And the reason we call it y is because now we establish an equation, and we can do the natural log on both sides of the equation. So I take the natural log of the left side, and then on the right side, you can pass the limit. Sorry, you can pass the natural log through the limit, and then you get natural log of n to the 1 over n. And the whole point of that was to do what? Use the property of logs that allows you to take that power and drop it out in front. That's just a property of logs from college algebra. So my next line is natural log of y equals, I'm just continuing this down, right? Natural log of y equals limit n goes to infinity. The 1 over n came out front, and I still have times natural log of n. I did this, I was covering this topic in my Cal 1 class that's right before this class. Last week, we finished L'Hopital. So yeah, it's fresh in my mind. I haven't forgotten. We're not taking derivative. Hold on. We got to figure out what's going on with this. Let's let n go to infinity. Where does this go? That goes to 0. Okay. And now what does this do? What does the natural log of n do as you go to function go off to infinity? It goes to infinity, and the natural log looks like this. Well, maybe not that steep, but it slowly goes up. As you go to the right, it goes up. This goes to infinity. So this in Cal 1 is called an indeterminate form. You can't tell what's happening here. And then this is also an indeterminate form in Cal 1, 0 times infinity, something big. You don't know what's happening. Pick one of these and rewrite it where it appears in the denominator. Let me do it, and then you'll see. Drop it, right? So I'm going to choose to drop the 1 over n below the natural log of n. In other words, I'm going to write it this way. I'm not really doing anything other than rewriting this expression so that the n goes underneath down here. Do you agree 1 over n times natural log n? You could almost slide that up there like that. Yeah. Check the limit one more time. As n goes to infinity, that goes to infinity. Down the bottom, infinity. Infinity over infinity. L'Hopital. You can't use L'Hopital any time before. Got to get it to there. How am I doing on time? Right. So up here, I'll just continue. So I have natural log of y equals. Now I'm about to apply L'Hopital's rule, so I'm going to go ahead and write down L. Okay, derivative of the top is 1 over n, and then derivative of the bottom is 1. And now do your limit again. For infinity is going to head to where? 0. 0, and 0 over 1 is 0. So you get natural log of y equals 0, right? And remember, we wanted to know what y was. So now you got to get log. How do you get rid of the natural log? Exponent, right? E like that. And then from there, the left side becomes y, and the right side is e to the 0, which is 1. So that's your answer. Seems like what? Yeah.
Like if you need to get wired, then sub n.
Oh, you could like natural log of a sub n, natural log of a.
Right, just treat it like, I mean, is a sub n actually that equation?
Yeah, but we weren't trying to find out what a sub n was. We were trying to find out what the limit was as n went to infinity of a sub n. So I wouldn't at the end here want to say my answer is a sub n equals 1. But a sub n is actually a sequence, not the number 1. Yeah, y is the limit of a sub n. Exactly. Yeah. Now what you could do is write this. You could write a sub n arrow to 1. Now that makes sense. Because that means, oh yeah, we were going to let n go to infinity and we get 1.
What did you do after you y?
I tried to get the y out of the natural log. So I applied the inverse function. Right? What's the inverse of natural log? What's the function that kills the natural log? The exponential. When you put the exponential together with the natural log function, they kill each other off, and you just get the y. So I want to talk about something real quick, subtly, and hold your question for a second, because I heard a couple of people, and I know. Oops. All right, let me. I'll say this. If f has an inverse, okay, f inverse, like let's say a function has an inverse, right? That means your function is 1. So I'm assuming we have a function that has an inverse. That means when I graph this, it has to pass the vertical line test and the horizontal line test. So it's got to look, something like that. That would pass both vertical and horizontal line tests. So to say you have a function and it has an inverse, when you draw it, it looks something like that. Okay. Why that's important is this. If I plug in an A, it will spit out f of A, right? Yes. If I plug in a B, it'll spit out f of B. And these will be different, right? These will be different answers. So if A doesn't equal B, then f of A doesn't equal f of B. If we have different inputs, we're going to have different outputs. You can never have different inputs and have the same output. We have to have this property to do it. Because I can give you an example that doesn't qualify. F of x is x squared. If I give you two things that aren't equal, do you all agree that 2 is not equal to -2? Yeah. 2 is not equal to -2, right? But what if I plug 2 into both those, into that function? What if I plug 2 and I plug -2 into that function? What happens? I'll get the same answer of 4, right? So 2 different inputs does not mean that I get 2 different outputs for this function, but that's not a one-to-one function. It's not invertible. It doesn't have an inverse. Point here, all right? So if you have a function that has an inverse, then if A doesn't equal B, f of A doesn't equal f. Similarly, you could argue this a different way. You could say if A equals B, right? If A is equal to B, if these are the same numbers, then you can say for sure that f of A equals f of B, right? If the inputs are the same, then the outputs have to be the same as well, right? Okay, so why am I saying all this? Because this step right here, that step right there, natural log of y equals 0. What is the next step that I did over there? What did I do? How do you say what you're trying to tell me to do? It's impossible for you to say verbally what you're telling me to do next. I'm not raising both sides to E. I am not doing E. What the hell am I doing? But that's an equation, right? So I want you all to look at it this way. What I'm saying here is that this is A and it's equal to B, right? And I'm about to plug a function, right? And the function that I have here is e to the x. Now, e to the x is 1-to-1 because when you graph it, it looks like that, right? So if you have different inputs, you have different outputs, right? If you have same inputs, you have same outputs. So if these two are the same, then when I plug that into E, it should be equal to what I get when I plug that into. So E with that plugged in must be equal to E with that plugged in. That's my next step. But I'm technically, mathematically, I'm not doing anything to this equation. I'm using the property of inverses that I can go from this line to this line. So even though in a lot of classes, and I'm a victim of it myself, when I teach it, I say, hey, look, we're just going to do E on both sides. We're not doing anything to both sides. We're using the property of the function and the fact that it's 1-to-1 to write the next line. It's a subtle thing, but it's important, all right? It's important for especially like math majors, all right? So this to here, I just don't want anyone to ever like walk out of this class and say, hey, yeah, my professor told me, yeah, all we did was like multiply both sides by E. Or, you know, like, or we took E on both sides. Okay. I say that, but this is what I mean. No, you're just using the 1-to-1 property of E to the. You're using the 1-to-1 property. That if A equals B, then f of A equals f. So if these two are the same, then if I plug these into, I could have used any function. From this line, I could have done any function as long as it is 1-to-1. I could do the next line. So function. Yeah, can we think of another 1-to-1 function?
I thought it was
X cubed is a 1-to-1 function. X cubed, I see your hand. X cubed is a 1-to-1 function. It looks like that, okay? 1-to-1. That means that I am technically allowed to do that cubed and that cubed, which I think y'all would do. And you would, what would you tell me you did? You cube both sides, right?
I thought the reason for doing it, because if you plug in a inverse with this original, you would y in this case, or x.
Well, that's why I did it. That's why I did. So the reason I did E, was because I wanted to kill the natural log, right?
Yeah.
So the reason, what motivated me to use E was the fact that I knew that it's the inverse of natural log. But the fact that I could go from here to here, I could have used any function that was 1-to-1 and do that and say that. It's just, it's not general. I have like 1 minute, 2 minutes. It's not something you can generally say. Okay, if I write down here, X is equal to 2. Okay. Now what I'm going to do is I'm going to take that expression that equals, and what I'm going to do is plug it into something that's not 1-to-1. So what's not 1-to-1? X squared, right? Okay. Let me do something not so obvious, because then you're just going to tell me you're doing sine. I mean, X squared on both sides. Let me do sine instead. So if I wrote this next line, is this true? Can I do this? Can I say this? It's true. Sometimes if X is 2, does that mean sine of X is equal to sine of 2 always? No. Okay, so it's tricky, but I just wanted to go off and just explain that a little bit. How do I want to say this a different way. No, I don't. I think I'm done. I think I made my point. Okay, so what I like for you to do for homework is wait. I'm going to go to my office right now. I'm going to look in this section. I'm going to pick what problems that I want you to do, because we can't do everything. We're still in 8.1. We still have more to do. And then next time we get 8.2. 8.2, we start talking about series. And then it starts getting real fun. Everybody have a great day. Check your email later for homework.